Hi, I'm Yingkai, and today I would like to share with you my work on tight bounds on simultaneous estimation of incompatible parameters with my colleagues Jasminda Sidhu, Earl Campbell, and Peter Koch while I was at the University of Sheffield. Now, the outline of the talk is as follows. First of all, I'll introduce you to the topic in which this project is based in, which is multi-parameter estimation. In multi-parameter estimation, one would want to estimate multiple parameters that are potentially incompatible. An example of a parameter that one could want to estimate in a physical system could be something like the position of a particle. And as one knows from quantum mechanics, estimating the position of a particle is incompatible with estimating its momentum. So one would want to know the minimum possible sum of the variances of all of the underlying parameters that one wants to estimate. And the Holevo-Kramer-Rao bound, which is what I'm going to talk about next, is the fundamental quantity that we're going to study in this research paper. And the Holevo-Kramer-Rao bound gives the minimum weighted sum of variances of the parameters that you want to estimate. And this bound is attainable in the asymptotic setting. Now, mathematically, this bound can be viewed from the lenses of optimization theory. This Holevo-Kramer-Rao bound is at its heart an optimization problem, where you minimize an objective function subject to some set of constraints. And because of this, we can use optimization theory techniques to solve this Holevo-Kramer-Rao bound optimization problem in some special settings. And when we do not have, and in a more general setting, we can also use optimization theory techniques to obtain fairly efficient algorithms for evaluating this Holevo-Kramer-Rao bound, which makes, and all this makes the evaluation of the Holevo-Kramer-Rao bound, which can be a potentially difficult problem, into a much simpler one. And after that, we'll talk about future work that can be performed based on the results of our work over here. So now let me share with you the problem of multi-parameter estimation. So one can have some parameters that one wants to estimate. For example, there's a parameter theta 1 and all the way to theta d. We have d parameters that we want to estimate. These are very general. One can think of them as for example, if one wants to estimate the magnetic field, one wants to estimate the magnetic strength in the z direction, the y direction, and in the x direction. And to perform this estimation in quantum metrology, we use something that's known as a probe state, and we denote it as rho over here. Now, rho will depend on the parameters that we are going to estimate, because if it doesn't depend on the parameters, this probe state is useless for estimation. So we want this probe state sensitive to these parameters we are going to estimate. And in particular, we want it to be maximally sensitive, and we want a probe state that's very sensitive to these parameters over here. And because in quantum metrology, we are interested in the sensitivity, issues of sensitivity, it is important to compute the derivatives of this probe state with respect to these parameters over here. And we denote these derivatives as follows. And the problem in estimation theory is, what is the minimum, for example, the sum of the variances that we could have when one estimates these parameters? Or in more general setting, what is the minimum weighted sum of these variances? And this is the problem that the Holevo-Kramer-Rao bound sets out to address. And Holevo proved that this minimum sum of weighted sum of variances is given by the optimum value of this minimization problem. The quantity that's being minimized over here is something that's linear in the Z matrix and something that is like the trace norm of the imaginary part of the Z matrix. And we have some constraints over here. And what is important about these constraints is that they are linear in the optimization variables X. The X's are essentially the observables that we are going to measure. These X's, because they are observables, must be Hermitian operators. And these constraints over here essentially are some normalization constraints, and also to set the and also some unbiasedness constraints. The Z matrix over here is simply a matrix that comprises of traces, and these traces depend only on the probe state rho and the observables axis that we are optimizing over. And for simplicity, in this talk and in the paper that we study, we set the weight matrix to be the identity. And so this objective function over here simplifies a lot. It's just the trace of the real part of Z plus the trace norm of the imaginary part of Z. And we make an important observation, is that by reparametrizing this optimization problem, we can simplify the form of this optimization problem. Namely, by letting y be equals to x plus rx2, we can have this simple form. And the advantage of having y instead of the x's is that, well, y doesn't have this Hermitian constraint. Y is an arbitrary operator. And we have this very compact form for the whole level Kramer-Rao bound for the 2-parameter setting, and in the case when the weight matrix is the identity. Now, in optimization theory, if you want to minimize a problem, which you could call the primal problem, there will always exist something that's known as the dual problem. The dual problem is going to give a lower bound to the optimal value that you want to find, which in our case is the whole level bound. And any feasible solution of the primal problem will give an upper bound, and any feasible solution to the dual problem will give a lower bound. The primal parameters in a 2-parameter setting will be this value t, little t, which is a real number over here, and y. And this y is a complex valued matrix. And the size of this matrix is essentially equals to the size of the probe state. And the dual problem has these variables over here. And these variables, we can call them dual variables, but they're also known as the Lagrangian multipliers of the corresponding Lagrangian to the primal problem. And over here, the z's are the dual variables that correspond to the linear constraints in the original whole level Kramer-Rao bound, and this u is an additional dual variable that comes up when because we recast the optimization problem in this form. And what we like to emphasize is that by using insights from optimization theory, for our case in the whole level Kramer-Rao bound, the dual problem is actually exactly solvable. And because the dual problem is exactly solvable, and it always is a concave function, it is easy to find the optimum solutions of the whole level Kramer-Rao bound, and also the optimum value. And this is the approach we take. It is well known that the optimality conditions in optimization theory are just the celebrated Karush-Kuhn-Tucker conditions. There are 4 such conditions. The first is that the derivatives of what is known as the Lagrangian are equals to 0. The second condition and the third are just saying that you have primal feasibility and dual feasibility. So now this Lagrangian is a function of the primal variables and the dual variables. So what we want for the optimality conditions is that when you pick these primal variables, they must satisfy the constraints of the primal problem. And also for the dual variables, they must satisfy the constraints of the dual problem. So these are kind of obvious. And the last condition is complementary slackness, which is a technical condition which we also use to simplify our problem. So what is most important is this stationarity condition, which basically says that the derivative of the Lagrangian is equals to 0. For us, the Lagrangian can be written as follows. It has some linear component and has some quadratic components. These quadratic components arise from the quadratic constraints that I was telling you about. And to show that the derivative is equals to 0, we need to show that it's 0 in all matrix value directions. So this derivative over here is really taking the Frechet derivative, a generalized derivative. So at this point, we have two approaches. We could, for example, pick y to be 0 or 1, u to be 0 or 1. In that case, this Lagrangian would have an extremely simple form, and it will be very easy to solve for y analytically. And once one solves for y analytically, one can solve for the dual problem analytically, and hence solve for the whole level Cramer-Rao bound analytically. However, the problem with this is that this when you set the dual variable to be equals to 0 or 1, this need not always lead to the optimal solution. It does, however, lead to bounds, upper and lower bounds, using the primal dual approach in optimization theory. If one, however, wants the optimum solution, one would have to look at this. One can show that the optimum solution of the stationarity condition of this Lagrangian is satisfied whenever y satisfies this equation over here. Now over here, A is just some matrix that depends on the dual variables z and also the probe state rho, and also the derivatives of rho. So we want to solve this general, and this matrix equation over here is known as Sylvester equation. And Sylvester equations are well studied in control theory, and that's why insights from control theory now we can see has implications in this problem of multi-parameter quantum metrology. So let's look at the case of u equals to 0 or 1. This is really simple. And so when we make this substitution, we derive the dual program, and we find that the solution, the optimum solution of the dual program must satisfy this equality over here. And this is really just a system of linear equations where these matrices are given in terms of the original problem. Over here, the A's are related. These AIs are just related to the probe states and its derivatives, and rho is just the probe state. So the only thing that we need to demand is that this probe state is full rank. So we can solve this analytically in many cases and obtain upper and lower bounds on this whole level quantity over here using the primal dual approach. Now, in general, one can attempt to solve this equation. And one can solve this equation if one has the spectral decomposition of the probe state. And this gives the solution, y is this thing over here. And using this solution of y, one can make the substitution back into the Lagrangian and get this thing known as the Lagrange dual function. And one can see that this Lagrange dual function is just a quadratic function in z. And because it is a quadratic function in z, one can solve it analytically, given fixed values of u. And this Q matrix over here is depending only on rho and its derivatives. And of course, this fixed value of u. So given a fixed value of u, we can analytically solve for the whole level Cramer-Rao bound. And so for any value of u, we have, in general, these primal dual bounds. We have upper bounds and lower bounds. And moreover, we know the condition on u for which we have the optimum solution by using properties from optimization theory. Namely, if this derivative over here is equals to 0, then we know that the corresponding value of u is the optimum value for the dual variable. So, in short, we have now given a new approach to this multi-parameter estimation problem by using deep insights from optimization theory. And we envision that because now the evaluation of the whole level Cramer-Rao bound becomes much more simpler, easier, and at many times analytic. These results can be used to give us new insights into, for example, problems like noisy quantum metrology, which is very important for us to have like quantum sensors that work in noisy environments. And also, this has deep ramifications in the optimum design for many different types of quantum sensors, such as those for sensing magnetic fields, or for example, for quantum imaging. And also, we envision that more optimization theory perspectives can further benefit the field of quantum metrology. And with that, I thank you for your attention. Have a good day. Bye.